Imagine you've just bought the most expensive, ridiculously powerful sports car on the planet. I mean, we were talking about a massive cluster of H100 GPUs.
Oh, yeah. The dream setup.
Right. But instead of flying down the Autobahn, you're stuck driving it in bumper-to-bumper traffic at like 5 miles an hour. That is exactly what happens when your autoregressive large language model enters the decoding phase.
Exactly. Your massively parallel compute engines are just, well, they're starving.
Sitting there doing absolutely nothing.
Yeah.
And you are entirely bottlenecked by the sheer weight of moving the key value cache, the KV cache, from the GPU's main memory onto the chip for every single token you generate.
It really is the defining systems engineering problem in generative AI right now because, we've successfully built these architectures that can understand immense amounts of context.
Right, massive context windows.
But during autoregressive decoding, memory bandwidth simply cannot keep up with compute capability. As your sequence length scales linearly, your KV cache scales linearly.
And your arithmetic intensity just plummets.
It plummets, yeah.
Yeah.
You hit a hard physical memory wall.
Which brings us to the source material for today's deep dive. We're looking at a July 2024 paper titled QJL, 1-bit Quantized JL Transform for KV Cache Quantization with Zero Overhead. It's authored by Zandieh, Daliri, and Han. And if you're serving LLMs in production, this paper might just be your ticket out of that traffic jam.
It is a rigorous, highly innovative mathematical intervention. I mean, it fundamentally rethinks how we compress representations in the attention mechanism.
Okay, let's unpack this. Our objective today is to map out the mathematical novelty of this QJL algorithm. We're going to examine the theoretical mechanics behind it, specifically this wildly creative asymmetric inner product estimator they've developed.
Which is the core of the whole thing.
Right. And then we need to bridge that theory into reality by looking at how they handle the chaotic distributions of actual trained LLM weights.
Yeah.
And finally, analyze the empirical system's performance. Because, spoiler alert, they achieve an 81% memory reduction in the KV cache without losing accuracy and without any latency overhead.
Which, mathematically speaking, is an exceptional claim. And it requires us to first understand exactly why the existing methods for compressing the KV cache are failing to achieve this kind of efficiency.
Right. So if I'm a machine learning engineer trying to deploy Llama 3 with a massive context window, I'm probably looking at current state-of-the-art quantization methods like KIVI or KV Quant, right?
Yeah, those are the standard go-to methods.
And they perform per channel or per token quantization, breaking the data into smaller blocks to preserve accuracy. But there is a massive, often unspoken tax with those methods.
Yes, the blocking overhead. To quantize a block of data effectively, say, down to 2 or 3 bits per parameter, you cannot just blindly truncate the numbers. You have to calculate and store quantization constants for that specific block.
Like a scale factor.
Exactly. Usually that means storing a scale factor and a 0-point constant so you can map those compressed integers back to their original floating point scale during inference.
And those constants have to be stored in full 16-bit precision.
That is the fatal flaw right there. When you amortize the memory cost of those full precision constants over the size of the block, it adds this invisible tax of about 1 to 2 bits per quantized parameter.
So even if you pat yourself on the back for aggressively quantizing your actual values down to 2 bits, your true memory footprint is closer to 4 bits per parameter because of the metadata.
Exactly.
And when you are fighting for every single byte of VRAM to fit a 100K context window, a 2-bit overhead is crippling. I mean, it completely dilutes the benefit of the quantization.
And that overhead is exactly what this paper targets. Their conceptual pivot is moving away from blockwise scaling entirely. They propose a data-oblivious solution.
Using randomized sketching techniques.
Right, specifically a Johnson-Lindenstrauss, or JL, transform. They use it as a preconditioning step before applying a brutal 1-bit quantization. No 0 points, no group-wise scales, just pure mathematical projection.
Wait, hold on. I need to push back on this right away. A standard JL transform is essentially just a random Gaussian projection designed to preserve the distances, the inner products between high-dimensional vectors.
Correct.
But if you take the output of a JL sketch and blindly quantize it down to a single bit, just a positive or negative sign, you completely destroy the magnitude information.
You do.
And in an attention mechanism, you're feeding these inner products into a softmax function. Magnitude isn't just important, it's everything. You can't just wish that destroyed information back into existence.
You are touching on the exact paradox that makes this research so compelling. You're absolutely right that mapping a projection to a single sign bit shatters the magnitude data. If you quantized both the query and the key in this way, your attention matrix would be garbage.
Just total noise.
Exactly. But the authors bypassed this destruction by introducing an asymmetric estimator. They fundamentally changed the rules of how the vectors interact.
Let's break down the mechanics of that, because this is where the paper gets brilliant. The algorithm generates a random sketch matrix. Let's call it S. This matrix is populated with independent, zero-mean, unit variance Gaussian variables.
Right.
Now, for the key embedding, which sits in the cache-consuming memory, the algorithm applies the projection and literally just takes the sign. So for every dimension, it only stores a 1 or a -1, a single bit.
But crucially, what happens to the query embedding?
It stays fully intact. For the query, they apply the exact same random projection matrix S, but they do not quantize the result. The query remains in full precision.
And that asymmetry is the secret engine of the entire paper. The estimator they build from this interaction is mathematically beautiful.
How does the math work there?
To estimate the true inner product between the original query and key, they calculate the L2 norm of the key, which is just one scalar value calculated and stored once. And they multiply it by the inner product of the full precision query sketch and the 1-bit key sketch. Then they scale the whole thing by a constant derived from the Gaussian distribution. It's the square root of pi over 2 divided by the projection dimension.
Let me try to visualize this geometrically. It's like trying to identify a highly complex object in a pitch-black room. If both the query and the key are just 1-bit shadows, you only get a vague silhouette.
Right, you get the shape but no depth.
Exactly.
Yeah.
You know they might be facing a similar direction, which gives you the cosine similarity or the angle between them. But you have zero idea how large the object actually is. And if you've ever tried to back out an exact, unnormalized inner product from just cosine similarity, you know it introduces massive statistical bias.
It does. A symmetric 1-bit quantization creates a fundamental bias that just ruins the attention scores.
But by keeping the query in full precision, it's like shining a high-resolution full-spectrum flashlight onto that 1-bit shadow of the key. Because you know the exact precise properties of the light, the query, you can suddenly deduce the exact size, distance, and magnitude of the object from its compressed shadow. The asymmetry is the flashlight.
That is a phenomenal way to visualize it. What's fascinating here is the mathematical proof for why that flashlight perfectly recovers the distance without bias. It's rooted in how they decompose the vectors.
The parallel and orthogonal component.
Exactly. To prove that the expected value of this hybrid estimator perfectly matches the true inner product, the authors slice the query vector into 2 distinct components. One component that runs entirely parallel to the key, and another component that is strictly orthogonal to it.
I see where this is going. Because the projection matrix S is filled with purely random, independent Gaussian variables, the projection of that orthogonal component is statistically independent of the key's sign bit.
Right, and because they are independent and centered at 0, the expected value of their interaction simply vanishes. The mathematical noise from the orthogonal directions completely cancels itself out in expectation.
Leaving only the parallel component. But how does the parallel component recover the missing magnitude? I mean, the key is still just a sign bit.
This relies on a fundamental property of the normal distribution. When you project the key through the Gaussian matrix, you get a normally distributed random variable.
Right.
If you multiply a normal random variable by its own sign, which is what happens when the parallel query component interacts with the 1-bit key, you are essentially taking the absolute value of that Gaussian.
Oh, I see.
And the expected absolute value of a zero-mean Gaussian is directly proportional to its standard deviation, multiplied by the square root of 2 over pi.
Which is exactly why the estimator formula includes the reciprocal of that constant, the square root of pi over 2. It perfectly scales the absolute value back up to the true standard deviation, which corresponds to the L2 norm.
Exactly.
The orthogonal noise evaporates, the parallel signal gets perfectly reconstructed using the statistical properties of a bell curve, and you arrive at a completely unbiased estimation of the inner product.
It is a masterclass in applying random matrix theory to neural network bottlenecks. But as any data scientist knows, being unbiased in expectation is only half the battle.
Right, because an estimator can be perfectly unbiased on average, but if its variance is wildly unpredictable, your attention scores on any given token are going to hallucinate extreme values. The math might work across 1 million samples, but an LLM needs it to work on this specific prompt.
Which brings us to the theoretical guarantees of the paper. Under Lemma 3.5, the authors don't just stop at expected value. They rigorously bound the distortion.
Oh, so.
By calculating the higher order moments of their estimator and applying the Bernstein inequality, they prove that the probability of the estimator deviating significantly from the true inner product drops exponentially as you increase the projection dimension.
And this is where I found a detail in the text that felt like a typo the first time I read it.
Oh, the distortion bounds.
Yes. How on earth can the distortion bounds for a 1-bit quantized estimator be tighter than the bounds for the original unquantized JL transform? That violates every intuition I have about information loss. You are throwing away 15 bits of precision per dimension, yet the math says the estimation becomes more stable.
It is incredibly counterintuitive, I know, but it reveals something profound about 1-bit quantization when paired with random projections. The quantization step actually acts as a regularizer.
Okay, break that down for me. How does losing information regularize the math?
Think about the tails of a Gaussian distribution. Occasionally, a random projection will yield a massive extreme value just by chance.
Right, an outlier in the projection at night.
Exactly. In a standard unquantized JL transform, that extreme random value multiplies directly into your inner product, causing a massive spike in variance. But the 1-bit sine function acts like a brick wall. It doesn't care if the projected value is 0.1 or 10,000. It clips everything down to a simple +1 or -1.
Wow.
It completely truncates the extreme tails of the random distribution, which artificially caps the maximum possible error on any single dimension, tightening the overall variance of the sum.
That actually makes a lot of sense. It dampens the extremes without shifting the central tendency.
Boom.
But the attention mechanism doesn't just use inner products natively. It feeds them into a softmax function. And softmax is notoriously sensitive to input perturbations because of the exponentiation. A tiny error in the inner product becomes a massive divergence in the attention weights.
The paper addresses this directly in Theorem 3.6. They prove that as long as the embedding norms are bounded, the relative distortion of the final attention scores post-softmax is tightly constrained. But the most important takeaway for systems engineering isn't just the error bound itself, it's what the bound depends on.
The scale and behavior.
Yes. The formula shows that the number of bits you need to store the key cache, which is determined by the projection dimension, scales proportionally to the inverse square of your error tolerance, multiplied by the logarithm of your sequence length. Notice what variable is completely absent from that equation.
The hidden dimension of the model.
Exactly. The memory footprint of your quantized key cache is entirely decoupled from the original embedding dimension of the language model. Whether your model has a hidden dimension of 4,000 or 40,000, the required size of the QJL sketch scales only logarithmically with the context length.
That is a staggering implication for future model architectures. But let's step out of the theoretical sandbox for a minute, because there's a massive assumption hiding in that proof.
The bounded norms.
Right. The distortion bound relies on the assumption that the embedding norms are bounded and well-behaved. If you look at the empirical data from real deployed models like Llama 2 and Llama 3, that assumption breaks down catastrophically. Here's where it gets really interesting.
You're referring to the outlier problem. It is a well-documented nightmare for quantization.
Exactly. In the early layers of an LLM, the attention embeddings look like nice, neat, normal distributions. But as you propagate deeper into the network, the model learns to push massive extreme values into a handful of specific, fixed coordinate channels. These few outlier dimensions dominate the entire L2 norm of the key embedding.
And if you just blindly apply a random Gaussian rotation to a vector that contains a massive outlier, that single massive value bleeds into every single projected dimension. It completely overwhelms the signal of the well-behaved features, destroying the theoretical bounds we just discussed.
So how do they fix it without reverting back to the blockwise overhead they were trying to avoid?
With a highly pragmatic dual quantizer framework, the authors realized that these outlier channels are persistent. They appear in the exact same coordinates across different tokens for a given layer. So during the initial prompt processing phase, they dynamically identify these heavy-hitting channels. They essentially separate the data into two streams.
The massive outliers and the well-behaved in layers.
Right.
And they process them differently.
Exactly. They apply two completely independent copies of the QJL quantizer. They allocate slightly more projection dimensions to the outlier stream to ensure those massive magnitudes are preserved with high fidelity, while aggressively compressing the inlayers down to 1 bit.
That's brilliant.
And then they just sum the two estimators back together at the end. It completely protects the mathematical integrity of the proof while dealing with the messy, chaotic reality of trained neural network weights.
It's an elegant engineering bypass. And speaking of engineering bypasses, there's another crucial implementation detail regarding the random matrix itself. Instead of just pulling pure independent Gaussians for the projection matrix, they apply a QR decomposition to orthogonalize the rows. It's called an orthogonalized JL transform.
Yes, the OJL transform.
Why bother doing that? Because in high-dimensional space, random Gaussian vectors are already nearly orthogonal just by statistical chance.
Nearly is the operative word there. If you draw random vectors, there is always a chance that some of them will clump together.
Which means you are essentially taking multiple pictures of the exact same angle of the data.
Which is a massive waste of your projection dimension budget. Every bit in your cache needs to be earning its keep. By applying a QR decomposition and forcing the projection vectors to be strictly mathematically orthogonal, you guarantee that every single bit of your sketch captures a completely unique, statistically independent angle of the embedding variance.
That makes perfect sense.
And it's a zero-cost operation because the projection matrix is generated once and cached. But empirically, it notably tightens the accuracy of the estimator.
Before we move to the final benchmarks, we need to address the elephant in the room. We've spent this entire deep dive talking about the key cache. We haven't mentioned the value cache once. Does QJL apply to the values as well?
It doesn't because it doesn't need to. The value cache plays a fundamentally different mathematical role in the attention mechanism. The errors in the value quantization are linear.
Right.
They don't get fed into the exponentiation of the softmax function, so a small error doesn't blow up into a massive hallucination. The authors found that standard token-wise quantization works perfectly fine for the value cache. They focus their heavy mathematical artillery exclusively on the key cache because that is where the nonlinear amplification happens.
All right, let's talk systems performance. Theory is fascinating, but at the end of the day, developers need to know how this runs on actual silicon. They set up their testing ground on a single A100 80 GAB GPU. They ran benchmarks against models like a fine-tuned Llama 2 7B with a 32K context window and the newer Llama 3 8B. What does the empirical data actually look like?
The long bench results validate the theory completely. Operating at just 3 bits per floating point parameter, which translates to an 81% memory reduction, or a more than 5-fold decrease in the overall KV cache footprint QJL, matches the exact full precision FP16 baseline.
Zero accuracy drop on a 5x compression. That is wild.
None. In fact, on complex, long context retrieval datasets like Narrative QA, Casper, and 2Wiki Multi-QA, it consistently outperforms existing methods like KV and KV Quant and F1 scores.
And the compatibility aspect is huge here, especially for modern architectures. Let's look at Llama 3. Llama 3 natively uses grouped query attention and operates on the BF16 data type. Existing quantization frameworks like KIVI rely on optimized kernels that only support half-precision floating point, FP16. They literally cannot run on Llama 3's native data types without costly conversions.
QJL, however, was designed to be native to these newer formats. Its lightweight CUDA kernels support both grouped query attention and BF16 out of the box,
making it currently the only method in this category capable of quantizing Llama 3 natively. And when they ran it through the standard LM-Evil datasets, tests like HeliSwag, PIQA, and MathUA-QJL at 3 bits didn't just match the baseline. On average, it actually achieved a slightly better accuracy than the exact 16-bit baseline.
That slight bump in zero-shot accuracy is almost certainly the empirical manifestation of that regularization effect we discussed earlier. The 1-bit quantization is filtering out the extreme noise in the key embeddings. But beyond the accuracy preservation, the most critical metric for production deployment is speed.
Right, because traditional methods like KD Quant are notoriously slow during the prompt phase.
Extremely slow, because they require heavy data pre-processing. They have to compute running statistics, identify group boundaries, and calculate optimal scaling factors on the fly before they can even begin generating tokens.
Which kills your time to first token.
Exactly. QJL sidesteps all of that because it is entirely data oblivious. There's no tuning, there are no running statistics to compute. You simply multiply by a static random matrix and take the sign. Because of this, QJL's prompting and decoding latency is virtually identical to the exact unquantized baseline. It gives you the 5x memory reduction for free without the latency penalty that usually plagues deep quantization.
Okay, to bring this all together and distill what this means for you, the listener, whether you are managing cloud infrastructure or running local models. What we have explored today is a fundamental paradigm shift in how we handle the LLM memory wall. The authors of QJL have introduced a data-oblivious, zero-overhead quantization framework specifically engineered for the key cache.
Which is incredibly needed right now.
Yeah, Absolutely. By leveraging an asymmetric, one-bit quantized Johnson-Linden-Strauss transform, they mathematically guarantee an unbiased inner product estimator whose memory footprint scales logarithmically with context length, completely decoupled from the model's hidden dimension. Empirically, they solve the outlier problem, deliver a five-fold memory reduction, and maintain state-of-the-art speed and accuracy across modern architectures like Llama 3. They have mathematically eliminated the blocking overhead.
Which is an incredible achievement for inference. But if we connect this to the bigger picture, it raises a profoundly provocative question about the future of how we build these models from the ground up. If asymmetric randomized sketching can so effectively preserve the vital signal of the attention mechanism while aggressively compressing the memory footprint during inference, could this exact mathematical framework be pushed backward into the training phase?
Oh, wow. Training natively in the sketch space.
Exactly. Right now, we train transformers using standard, exact, and squared attention matrices, and we only try to compress them after the fact to make them deployable. But if this math holds true without any parameter tuning, could we train architectures that natively project their keys into one-bit spaces from day one? If we could bypass the massive memory constraints of full precision attention during the backward pass, we could unlock context windows during training that would make today's models look microscopic.
Which means all those idle GPU threads sitting around in traffic starved for memory bandwidth might finally be unleashed to do the math they were actually built for.